Okay, I think we can slowly get started. So let me introduce today's speaker. Yeah, first of all, thanks very much everyone for coming again to our seminar series. Today we're going to somewhat continue the topic from the last 2 weeks, which is going to be unlearning, but from a different perspective. So today we're going to hear about it from the perspective of mechanistic interpretability. And we're also going to dive into, yes, we're going to record it, yes. And we're also going to dive into a bit of a different type of AI model, which is diffusion models. Okay, so on this note, let me introduce to you today's speaker, Kamil Deja. Kamil is a team leader at the Ideas Research Institute and also an assistant professor at Warsaw University of Technology. His research centers on generative modeling with a particular focus on diffusion models and their applications. He has international experience at institutions such as, I'm not sure how to pronounce that, but Amsterdam, La Sapienza in Rome, but also Amazon Alexa and CERN. Finally, he was awarded the FNP Start Award for one of the top 100 young researchers in Poland. And today he's going to tell us about SAeUron or SAeUron. Again, I'm not sure about the pronunciation, so please correct me. Interpretable concept learning with diffusion models with sparse autoencoders. Thanks very much, Kamil. Please go ahead.
Thank you very much for this introduction. I hope you can hear me well, and I guess you can see the screen. Yes, so I'll be talking about our methods, basically the work of my brilliant PhD student, Bartosz Seliński, which we call SAeUron, and this is a work on how to make diffusion models safe, so how to make them not, how to unlearn from them some concepts that we don't want them to be able to generate. Okay, so let me start with the introduction. It will be a bit different as you might expect. So I'll be talking a lot about generating images, but this particular one is actually a real image from a Belgian painter, René Magritte, who presented it in 1929. And as you can see, this is a painting with a title, and the title says "Ceci n'est pas un pipe," which translates to "This is not a pipe." And when Mr. René presented this painting at the exhibition, people were quite shocked, and he even said that they were quite outraged at him, saying, "Come on, dude, this is clearly a pipe. What's going on? What do you mean?" Well, and the answer from the René was, "Okay, if this is a pipe, so try to fill it with tobacco." And so the point here was that this is not a real object. This is some form of representation of an object that we all agree that, okay, this representation is actually for us the same as the concept itself. So I'm talking a lot about this kind of representations today, and mostly about representations inside of the bigger models, bigger neural networks. And I would like to try to explain to you whether we can try to all figure out if there are some representations inside of those big models, and that we can all agree that they are the same for us as the object itself. Okay, and so how can we actually try to approach it? Let's take a big neural network, which has, like, let's say, dozens of layers. Let's make it not that huge. Well, those layers are just matrices that we multiply the activations to get another activation and so on. And can we somehow guess whether in the activations, somewhere in the middle of the model, can we try to guess and find the representation of, for example, a given pipe? So if we have those dozens of different layers, can we say that, okay, after the 7th layers, if we have this type of this set of numbers, or to be more precise, this vector, can we say that this vector is actually a vector of a pipe? And to answer this question, you can adhere to this, what is called the linear representation hypothesis. And this is this hypothesis that says that in those models, high-level concepts are represented linearly as directions in the representation space. So the hypothesis says that even such a complex concept as a pipe should be represented as a linear vector somewhere in the high-dimensional space inside of the neural model. Okay, so if this is a linear vector, that sounds quite cool. That sounds quite easy to figure out. So it means that we can easily, we should be able to easily understand the insights of the model itself. But the problem is that the way how we train different neural networks is we basically try to optimize it to predict the given answer. And the simplest way to achieve the goal, it doesn't matter whether the goal is to generate an image or predict the next token for language models or to classify whether this is a cat or a cow. And the simplest way to somehow learn valuable information is to do it by compressing the input into some lower dimensional form, let's say, in terms of images at least. That can be that can entangle different informations into this lower dimensional form. So because of the compression that we have, we cannot actually easily find those linear directions. And it's not that simple that if we have linear layer with 1,000 layers that predicts that we can say that, okay, so the first neuron will be encoding the information about the pipe, and the second about the cat, and the third about the dog. The problem is that neural network has to encompass a lot of different concepts at the same time. So it will probably do it by compressing them into the form that, okay, first and third and 965 concept, if pointing in this direction, they will encompass, this will be the direction of the pipe, but third and 15th and 95th neuron, if pointing in a different direction, this will be a dog. So we have this, what we call superposition, where different neurons encode information from about different concepts, kind of compressing them all into this latent space. But we know that those concepts exist, so we can somehow try to decompose them. And the way how we can achieve it is, and the way how we did it in our work that we're talking about in a moment, is by training sparse autoencoders. So basically, we wanted to learn the sparse dictionary, which is the you can think about it as a real like a dictionary, like the book of concepts in this case, where you have where you take the activations which are in superposition. So those activations in here, for example, and you can what you can try is what we want to have is the composition of those concepts of those entangled features into a dictionary, so a large latent space of individual concepts. Okay, and what we what we use in here is sparse autoencoders. So you can think about them as basically the simplest autoencoders that I guess some of you might have, most of you might have heard about already. Models that are trying to produce exactly the same outputs as they are presented as an input. So we take some input, we pass it through the model, and we expect to have as an output exactly the same as we get as we put there as an input. In terms of sparse autoencoders that we've used, those models can be extremely simple. We're talking about the linear hypothesis, so those are just one linear layer here and one linear layer here. And And what I already told you is that we want to learn a very big dictionary of different concepts. We want to somehow be able to decompose those complex concepts into a set of individual concepts that are not necessarily independent, but somehow interpretable. This would be the best scenario. So what we can do, how we can do it, is we actually make this latent space actually huge, so a few times bigger than an input. You can think about it as like thousands of concepts, or tens of thousands, or even more. And we train the model to take those activations, to take those activations and code them into the latent space, and decode them back into activations, while at the same time we train the model to in a way that we regularize the latent space, so that it's each of the activation is encoded only with the limited number of features in the latent space. We can do it either with a simple L1 loss on the latent space, or with a top K feature selection. This is what we did. So basically, whenever we encode one set of one activation vector into the dictionary, we select only the top K activating features that we use to reconstruct those concepts. So with this top K selection training, we'll end up in this situation that the model will train to encode which activation with a small number of features that will be very descriptive for this particular activation. And for another activation, it will select totally different features, which will be very descriptive for this another activation. And the cool thing is that while those sparse autoencoders actually exist for decades, and now people thought, okay, so let's train them really on the activations inside of those large models, like large language models or VLMs or multimodal LLMs and things like that. And those applications in those models are actually quite popular right now. And what we thought with Arctic was that maybe we can go further. Okay, so our thought was we can take diffusion models, like the one diffusion model that you have. You should have heard the. Sorry, I can. So it was Borger saying one does not simply disentangle diffusion features with sparse autoencoders, and Gandalf was responding that what about SAeUron? He can do it. Sorry. I won't maybe not waste too much time on me trying to fix the audio. So we are thinking, okay, let's try to somehow disentangle diffusion features with sparse autoencoders. In this particular use case of making the diffusion models safer by unlearning concepts that we don't want. So you can think about it that the use case is pretty straightforward. If you are a diffusion model provider, you might end up with situations that users will ask, okay, generate me a photo of a naked Angelina Jolie, and the model should be able to actually, normal model without any preventing methods will probably be able to do it. There is this whole branch of research that is called machine learning that tries to somehow unlearn those concepts that we don't want. I remember there was a talk about unlearning LLMs 2 weeks ago, so I guess it might be familiar to you. So in the case of diffusion models, we want to be able to unlearn specific concepts, like for example this nudity, or in this case that you can see in here, the specific style, like for example the style on the left, which is the cartoonish style. While at the same time we want the model to be able to, of course, generate all of the other things. So we don't want to destroy the model in total. So what we did in here is we we wanted to use those sparse autoencoders to actually block features that are somehow, those disentangled features that are somehow connected to the concepts that we want to unlearn. So that during inference, when we block those features, the model won't be able to actually generate what the user asked about. And there are 4 steps in which we actually did it, and I will guide you through those steps one by one. So starting with the layer localization. I told you that we can train sparse autoencoders on the features that are extracted from a certain layer of the model. And if we take even like the old stable diffusion model, it already has like 9 different blocks of layers, so quite a lot of different layers. And we have to somehow select the single one that we want to intervene on. So what we did in here is we wanted to somehow find which layer, or which block in this case, is responsible for putting into the representations valuable information from the prompts. Because so it turns out that, for example, the first block and the last block are more or less responsible for changing the representation into images, or images into representations. So they are not really using, for example, the information from the prompt. Well, there are some particular blocks inside of this quite big diffusion models that are responsible for different things. Like, for example, in this case, we found that there is one attention layer that is responsible for taking the information about the given style from the input and applying it to the image. So what we did in here is we went one by one, block after another, or layer after another, and we substituted the output of this layer with an input of this layer. So we basically skipped this layer. And it turned out that if we skip this particular layer, there was no more information about the style in the images. So even though we wanted the case to be in the cartoonish style, they turned out to be quite normal. If we did the same with a different block, it didn't happen. The block was responsible for something else. So we simply went one block after another, and we found which layer is the most interesting for us. We took this layer, and then we applied sparse autoencoder after this layer. So what we did is we took the diffusion model, the frozen diffusion, pre-trained diffusion model that was able to generate many different things, and we prompted it with I think 50,000 different, maybe not 50,000 different prompts, but we prompted it 50,000 times with some different prompts. And we collected the activations after a given, after the selected block. We collected those activations, we put them somewhere aside. And then we took those activations and trained the sparse autoencoder using those activations. The cool thing is that if you think about okay, maybe this will be a bit more technical, so I'll just mention it, but don't worry if you don't understand it. The diffusion models usually use those architectures that are called UNet, and okay, even in the more common diffusion transformers are right now it works in a similar way. If you think about the image, the representation is actually not of this emo here. It's not a one vector, but it's like a vector for each part of the image, for each part of an image. So it's three-dimensional, it's not flat. So what we did is we took the representation of individual, let's say, pixel in this space as an input to the size. So we trained it on the representations of individual. You can think about of those individual pixels, which actually correspond to a few pixels in the original image. So this is just a detail that is quite important because we later on it enables us to actually interpret those features. But the most important thing is that we took the frozen model, we collected activation somewhere from the middle, and we trained the Sparse Autoencoder to disentangle those complex activations into a dictionary of I think 50,000 features, something like that. Okay, so when we did it, after we did it, we had to select which features we are okay for us and which are not. So let us assume that, for example, we want to unlearn frogs, but at the same time, we definitely don't want to forget how to generate dogs. So we sampled we took the activations that corresponded to the samples of frogs and activations corresponding to dogs. We encoded them all with our pre-trained Sparse Autoencoder, and some features. We saw that in this huge dictionary, there are some features that only activate for a frog, and there are some features that only activate for a dog. There are some features that don't activate for both of them. There are features of totally different concepts, or there are features that activate for both of those concepts. So in our case scenario, we were only interested in those features that actually corresponds to the concept that we don't want to be able to generate, but at the same time, we didn't want those features to activate for any other concepts that we didn't want to remove. So we just did this simple feature selection method like this, and we went on to the final step, which was interventions during inference. So now, what we did is we took our pre-trained Sparse Autoencoder, and we applied this exactly, and we basically connected it with the model, and now whenever the model was going through the synthesis step, we went to this Sparse Autoencoder, and we wanted to unlearn frog. We were selecting those features that we decided that are important for a frog, and we multiplied them by the negative multiplier. We can think about it. We could as well just simply block them, but this negative multiplier turned out to be even better. And we took those features and decoded them. Decoded then this dictionary with the Sparse Autoencoders decoder. And then the generation process went on as it did before. So now, in this scenario, as you can see, if we wanted to generate a frog, so the model wanted to generate a frog, but then we blocked the features corresponding to the frog. So it altered the activations inside of the model, preventing from generating this frog. And at the end we didn't, and the frog was not visible. But at the same time, if we wanted to generate a dog, we would encode the features with an encoder, and then those features important for frog would not be important for dog. Even though we will multiply them with the negative multiplier, and 0 times negative multiplier is still 0, so the dog would be generated without any problems. And this is what you can see in here in those results. So for example, here are the different concepts: trees, frogs, and sandwiches, and those are in different styles. And there is a known benchmark to unlearn either different objects or different styles from the stable diffusion model. So for example, in here, we wanted to either unlearn trees or frogs or sandwiches, but at the same time, we wanted to be able to generate other objects, so for example, and other styles also of the styles. So what you can see in here is that when we wanted to unlearn trees, the model was not able to generate trees, but dogs and sandwiches were generated without any problem. And when we wanted to unlearn frogs, the other objects were okay. When we wanted to unlearn sandwiches, the other objects were generated. and also the other styles, and the same style was generated without any problems. And the same worked for style unlearning, where we were able to remove the style without affecting the other styles or the objects. And the very cool feature that kind of makes this work more interesting than the other approaches is that we could really interpret what we unlearn. So this is why I wanted to mention those three-dimensional activations inside of the model. We are passing them one by one to the Sparse Autoencoder. So we could actually connect which activations inside of the model correspond to which pixels in the original image, and highlight, okay, so if we pass this activation through the Sparse Autoencoder, it activates feature number 963, and this feature is important for us, so we want to block it. So this feature is actually this feature in here, and only those patches inside of the activations corresponding to those pixels activate this feature number 963. So we could really highlight which are the features that we want to unlearn. So in the case of cat, that you can see in here, we only multiply by the negative multiplier those features that were activating in those areas. So you can see that those were probably features of ears, of cat whiskers, of cat paws, and another feature for cat ears. So you could really show that, okay, if you want to block the possibility of generating a cat, what we will be doing is we will block the possibility of generating those ears, those whiskers, and paws at the same time. And this will prevent the model from generating cat. Okay, and another interesting thing, when we were presenting this work at SAeUron, there was one guy who came to me and said, okay, so if you can use those features to steer and block the generation of something that you want to unlearn. I was talking about the nudity at the time. He was like, if you can do it one way, you can also do it another way, right? So yeah, so the answer is we can do it. And if you think about it, there are people that try to unlearn something from diffusion models. There are always people trying to then attack those models and try to adversarially still generate something. So in this case of nudity, when you there are some examples that if you take many different unlearning methods and unlearn nudity, then if you ask for a naked woman, the model won't generate the naked woman. But if you alter the prompt with some adversarial attack to some gibberish, it will still generate all of the nudity you want. The cool thing is that since our method was working directly on the activations of the inside of the diffusion model, it doesn't matter how we change the prompts, the features will be blocked. So our model was not really affected by this adversarial attack. So we were so the model was not able to generate those features that we wanted to really unlearn. And another good feature is that we can actually unlearn multiple different concepts at the same time, because we simply block more of the features from the Sparse Autoencoder. And since the dictionary was like 50,000 features, if I remember correctly, maybe a bit less, but still, if we were blocking 5 features or so, we could do it for multiple concepts without really hurting the performance, like the general performance of the model. Okay, so that's all regarding this basic work that I was wanted to present. So this summer method where we wanted to unlearn, but there is more. So I told you so far about the images, the thing that we discussed in today. So we can see that this is basically the summer method where we try to figure out which features correspond to what features, which features inside of the model corresponds to which features in the images. But diffusion models, I would say they are pretty cool. And they're pretty cool in many different domains. So we are now trying to move on to different domains, and what you can see here is that we already tried to, for example, use very similar concept that I presented today to steer the generation of the proteins. So I don't know if you know, but the newest protein models are also based on the diffusion process. So we can actually use exactly the same procedure as in here to steer the generation of proteins. You can see in here, what you can see in here is that we wanted to change how many alpha helices we have here. So those pink spiral things. And depending on how much we steer towards the selected features, we have less and less of those helices and more of what is called beta sheets, so those bluish straight objects, straight connections. This is one domain. Second domain that you won't hear because the audio doesn't work is that we also try to use Sparse Autoencoders to steer generation of speech and audio. Okay, you won't hear it, but you can maybe believe that. But believe me, that there are some different intonations in here. And diffusion models are also used for many other domains, like for example video. In here, another great PhD student found a feature of a big fish in the video generation. And another student was interpreting the waves of the diffusion model itself and found a pretty hot feature that you can see in the final image. Okay, and so that's all from my side, and I'll be happy to answer any questions. But I wanted to also mention that also at Thursday, every second Thursday, we have something that is called that we call the Diffusion Papers Reading Club. If you would like to learn more about diffusion models, it's open to everyone. So please join us. Maybe I'll just send you the link later on Slack and so on. Yeah, so that's all, and I'm happy to answer any questions if you want.
Yeah, cool. Thanks very much, Kamil, for this interesting and clear presentation. I have to say I found the connection to the biological models particularly interesting, because of the concerns about people misusing sequence models and kind of stuff. Yeah, so please let's give Kamil a round of virtual applause with emojis as always. And yeah, we're gonna turn to questions now. So feel free to unmute yourself or just raise your hand. Yeah. Can you see the questions in the chat, Kamil, or should I read them out for you?
Yeah, so let me read the question. You mentioned protein folding models in the what's next section. Why is machine learning interesting there to avoid generation of harmful substances? So it's not necessarily unlearning what we are trying to do there, but more like precise generation. So if you think about text-to-image models, for example, even there, it's actually quite hard to generate what we really want. You can write the prompt, generate me a photo of a cat, but then the cat will be in the wrong position, in wrong place, in wrong color. So it would be cool to have a mechanism to very precisely steer towards what we want to achieve. In protein design, it's even more complex because there you don't have even prompts. You might have some signals that you use for conditioning, but they are not very precise. And sometimes what you want is, for example, for this part of the protein to have a special part that is even not in the sequence but in the structure that will allow it to attach to a different protein or something like that. And you cannot really condition the model to generate it. But if you find the features that actually correspond to this, then you can steer the process to generate exactly what you want.
Okay, any other questions? Okay, I have a question myself. So this method, as interesting as and effective as it is, for me, like it doesn't satisfy the formal definition of unlearning, the classical definition, because you're not changing the weights in a sense, right? You're freezing the model, and it's kind of a deployment time intervention. I was wondering if there's any way of turning this deployment time identification of these SAE latents into like a permanent deletion of knowledge from the weights.
Yeah, so first thing is that I was actually the one who was more skeptical about it than Bartek to call it unlearning even. So I share your point. But then I started to dig up how the machine learning was defined. And actually, the first paper that used the term was very similar to what we wanted to do in here. Of course, not with Sparse Autoencoders. It was a paper from the 70s when they wanted to train an additional layer that, in order for them to be able to turn off some of the neurons during generation. Yeah, so it kind of fits, but I understand also your concerns more like if you, for example, want to do it on open model, then it doesn't make any sense because if you share the weights with the model that kind of with this part of the encoder inside, that people just can turn it off, right? But we haven't tried it, but we'll think about it later on. That actually what we should have done was that if you think about in here, if you think about what we actually want to do is we select a few features which are basically few vectors in this sparse sparse autoencoders decoder, and we multiply them by the negative multiplier. So we basically steer the activations with the linear vector, which is a combination of those few features, which is just one vector, right? And we do it after some previous some layer. It doesn't matter. It's probably some linear layer, the output of the cross attention layer. So what we can actually do is we can take this cross attention layer and simply multiply it by the vector in here, and substitute the weights of this cross attention layer of this layer with the output weights. So it will be like a permanent solution to always block the generation of shocks.
I see. Okay, thanks. That's interesting. Is that something that people use in like normal LLMs with SAEs?
I haven't heard about it. They should have, but I don't know if they do. So the other option would be to simply use transcoder, right? And then you don't have, you can have it simpler, let's say, because then you just decompose them, the whole matrix, the one matrix itself. So you can easily substitute this with, you don't have to multiply it, but it's basically the same concept.
Okay, cool, thanks. Yes, anybody else with a question? Yes, go ahead.
Okay, I had trouble understanding what you were saying. Can we? What are the limitations of the work? That was the first question, and the second, if I understood correctly, or and the second one, I didn't understand. Can we? Oh yeah, no, it's not better. Sorry, can you just repeat? Hmm. So the limitations are well, the first limitation we already discussed with Jakub, that it's kind of more like blocking. We haven't tested this idea with updating the weights. Second limitation is, okay, if you think about it, when we try to unlearn dog, or this cat that I showed you, so I was showing that, okay, that there are some ears, there are some whiskers, but then if you want to generate a tiger, it won't have whiskers. So there are some concepts that are that will be affected as well. So this is the problem of all of the learning methods. So, for example, in the background that we used, it was always the case that whenever the method tried to unlearn the cat, dogs were the ones that were the most affected because of the similarity. So it's super hard to be very precise. And regarding the unlearning itself, it's quite a very tough subject. So right now, the very interesting problem that we also tackle with another PhD student is that if you apply some unlearning method, you basically take the model and you kind of steer it away from the original flow, let's say, from the original value of the optimized weights, let's say. let's try to imagine that you are somewhere in the optimal weights point and you kind of go in some direction. And that is very strange in terms of all the statistics and things like that. So when you take this model and you do whatever with it, for example, you fine-tune it on benign data to tell you something different, then you can see the resurgence of the concepts that you unlearned. And there were some papers showing that. This is another problem with unlearning that we haven't solved yet, and I think we are still pretty far from actually solving unlearning.
Okay, thanks. We have a question from Maria in the chat, and I will read the question aloud so that it's audible in the recording later on as well. So Maria asks, hi, thanks a lot for the presentation. Could you explain a bit more about the last use case you presented? I believe it was speech and audio models. What exactly was the goal of unlearning there?
Yeah, so it wasn't unlearning. Okay, you can hear it, so I will stop it. It was also about the steering. So what we were trying to do is to so I was working with text-to-speech models some time ago, and what I wanted to find in here was to decompose some of the activations inside of the diffusion models that is used for text-to-speech, and try to find, are there any concepts that are interpretable that we can actually somehow use to change the output. So in this case, I found features that corresponded to the intonation. So I was able to, by steering with those features, changing those features in the same way as we did in here in order to block. I was able to change the intonation so it was more like a question or more like a sentence, something like this. So it's not about unlearning, but more about precise, like disentangling features into this sparse dictionary of features that are somehow interpretable that we can use to make the output exactly as we want it to be.
Okay, cool, thanks. Any other questions from the audience? Yeah, go ahead, Marcel.
How frequently did you find features which are not like clearly interpretable to humans?
Most of the time, I'd say, probably. Yeah, so it all depends on how on the Sparse Autoencoder that you trained, how well have you trained it, or more how well have it trained itself. Has it trained? The problem is that you have there are some features that are dense, for example, that activate for many different objects. We try to avoid them as possible, but of course they might happen. So in this case, those features were not really interpretable because there were just features corresponding to the activations of most of the images in the data set. So it was just a feature of an image, or I don't know, some features of frequencies or things like that. So it happened a lot in terms of I was playing a lot with this audio. So there, I had really hard time to actually find features that kind of correspond to human interpretable features. So it's not that easy as you can, as people sell it. Let's say it's hard to really train this Sparse Autoencoder to work as precisely as we want. And that's why this use case was actually pretty simple, because here we had this ground truth that so we could simply find those features that correspond to the one concept but don't correspond to any other concept. So with this kind of supervision.
Another question answered, or?
Yes. Have you tried to because you're talking about that you're talking that one of one of your goals is to be able to steer these models more usefully. So have you tried to compose some kind of image that would be really hard to prompt using this addition of activate of features?
So there was, for example, a very nice work where basically using the same principles that we did, what people did was they then created a tool where you can select the area in the image and select which feature from the Sparse Autoencoder you want to have in this area of the image. So you can actually generate a precise image where you have a lion in this region of an image, and a zebra in here, and the tree in here, using those features. So I'm 99% sure that if you just prompt for the lion on the left and zebra on the right and tree on top of them, you will end up with one lion or zebra without the tree or something like that. That's what usually happens.
Okay, cool. Any other questions? Yep.
So we use the biggest models that we could find, basically. They are usually smaller than LLMs because they are operating on higher dimensional activations, right? You cannot have so many parameters because you're basically processing the whole image at the same time. So I think that the biggest was an SAEXL model, which was I don't know how many parameters. 2.6 billion or 6.6. Never mind. Something like that. But there are none, it's already like one of the biggest models that you can find. And regarding the switches between different sizes, so we of course we train different Sparse Autoencoder for different models. And basically it works the same way. But the cool thing is that there are some models that are, for example, distilled versions of the big models. We haven't. We've tried that. We've tried with crosscoders that there are some features, for example, that you can learn that are common for those distilled models and those global original models. So it seems that you can use the activation from the original models to. You can steer the distilled models with the features from the original models, for example.
Right. I'll also allow myself to ask a second question then. Yeah, also slightly more like theoretical question, less about the details of your method. But yeah, I don't know much about diffusion models. I'm also not a Macinterp expert, but I've heard people talk about things like feature splitting, feature absorption, some more like theoretical problems with SAEs and so on, right? And I was wondering if there is anything specific to diffusion models that makes interpretability on them somehow different from LLM interpretability. So, for example, you were talking about this detail where you have a patch of the image, so actually it's not like a 2D thing that you're analyzing; it's a 3D thing. Does this affect things? Does this reduce or augment your interpretability abilities and so on?
Yeah, so this is definitely one of the different. Since one of the important difference is that it's really not 1D basically or 2D. And we have one more dimension, which is diffusion timesteps, which adds even more complexity to that. So I think this is the reason why it's not so popular yet, because it's much harder.
Wait, so sorry to interrupt. So for video generation, you have like a 5D tensor?
You have okay, it depends from model to model, but if you assume that, for example, you want to generate one, let's say 5 seconds of the video, it's the video itself is 4D, right? And because it's so this is so you have the activations are also 4D.
So 4D, but then you also have the steps in the diffusion process for each frame, right?
Yes. So it's getting messier and more activations. But I think it's just a huge opportunity for further research in there, because we can take what we have in LLMs and apply it, and this is what we did more or less. But we can also have some specific methods designed for images, and there are a few cool things that we are trying to tackle right now that might be more specific for interpreting in diffusion models and in image space. That doesn't make sense, for example, in LLMs. There was one paper, for example, I find it very interesting, where they tried to train sparse autoencoders, but not to reconstruct the activations inside of the model, but to try to reconstruct these activations that will result with the same output at the end. So propagating the gradient through all of the network. And it turned out that it didn't work really, because those features were super adversarial, because the model was able to, it's just a classification at the end in LLMs, the classification of which token to choose. So it was very simple to learn features that will trigger those specific outputs, but not learn anything meaningful. And in terms of diffusion models, where you have to output the whole image at the same time, not just select one of a few options that you have in the classifier. You have to predict the actual value of the pixel of the color. You have to learn meaningful things. So this is, for example, one idea that I'm kind of pursuing to train this kind of sparse autoencoder that will not learn features that are important to reconstruct activations, because most of them will be not important for the output. But to try to reconstruct those features that are actually useful for the final generation.
Okay, thanks. Any last questions, since we're closing on the hour now? Okay, if not, then let us thank Kamil once again for persisting with us through all these questions. So once again,
I'm always happy to answer any questions. If you have any further, please just roll to Slack.
What we usually do is we create a thread on Slack, and then hopefully, if you're available for further questions, I'm going to write them there. Yeah.
Sure. I'm happy to answer any questions. And if you are interested in these topics, I'm always happy to also collaborate with whoever wants to.
Cool. Thanks very much. Before you all drop off, I'm sending right now the link to the next seminar in the chat. It's going to be, as always, in 2 weeks' time on Thursday. And then we're going to hear from Tomek Korbak about yet another topic. It's going to be on chain of thought interpretability. So we're switching from topic to topic, but this is good because we're giving, hopefully, you the overview of different areas of AI safety. Okay, cool. Thanks very much, everyone, for coming once again. I hope to see you in 2 weeks' time, and have a good evening, everybody.
Thank you, and see you.